in Chapter 2, we talk about electric field, and I want to go over some of the topics or things that students find difficult in this chapter. And so the first thing I want to talk about is the difference between electric field and electric force. We've already learned a little bit about force, and let's just review for a second. If we have a big negative charge here, and I bring in a little positive charge, I want to know what the force is on this positive charge due to the negative charge. And so I know, since this is positive and this is negative, that this positive charge is going to have a force on it that's this way, towards the negative charge. So the negative charge is going to be pulling it towards it. So I'm going to have a vector that looks like that. This one's pulling towards that one. And if I want to look at this one, this big charge has a force on it due to the positive charge, right? And it's going to be towards the positive charge. So force vectors are a lot like velocity vectors, right? If I'm walking along, say I'm walking along this way, and this is me, and I'm walking along this way, I can draw a vector for velocity, and it would be in this direction. So this would be my v vector, where these are my force vectors. So what about field, though? So let's forget force for a minute and talk about field. And so now let's pretend that this charge is no longer here. Let's cross that out. This negative charge still has a field, right? I don't need a positive charge here for this negative charge to have a field. So while force is a vector, force is a vector in one direction only. This negative charge, however, is a vector too, but it has direction depending on where you're looking. So if I think about the field, if I want to know what the field is due to this negative charge out here, right? I know it's going to be pointing towards the negative charge. And if I want to look here, I know that it's going to be pointing towards the negative charge. And if I want to look out here, I know it's going to be pointing towards the negative charge. So as I continue to draw arrows here, right, I'm defining this field of this negative charge. And notice that the field of this negative charge, it fills the space. So I would have a much bigger vector representing, right? It would be a matrix for any point in space, any x, y, z coordinate around this charge. I will have a field. And so while the force vector is a very simple vector, only in one direction, this is more of a matrix for the electric field. So I just wanted you to understand the difference between those, the vector representation of those two things. Now, we learned in this chapter that the electric field is the force divided by the charge. So we can find the electric field if we know the force and we know the charge, and vice versa, we can find the force if we know the charge and the electric field. And then we can also use Coulomb's law, right, to find the electric field. And so we have 1 over 4 pi epsilon naught times q over r squared. So p would be the location where I'm looking. So if I have a charge, say this is my positive charge, call this C, and I want to know what the field is at this point. My RPC is the vector going from C to P. So that's what the RPC represents. And if Q is positive, then the E points away, and if Q is negative, then E would point towards the charge. Oh, this should be towards. This should say less than, and this should say toward. Okay, one more thing that I want to go over is they explain in the book that sometimes we might want to use a different method to calculate our electric field, because vectors make it a little bit easier to calculate the electric field, mostly due to the displacement vectors. So if we look at our equation, right, E is equal to 1 over 4 pi epsilon naught, and remember this quantity here, right, is just K. So if you like to think about it as just K, that's fine. Q over R squared, R hat. Now R hat is a unit vector, and that unit vector means that it has a length, right, it only has a length of 1. So it's just showing you the direction. And if we have a unit vector, that's given as an R vector divided by the magnitude of the R vector. So think about it like this. If I have a vector like this, where this is my R vector, right, then if I wanted to draw my unit vector, it would look something like just like that, where this would be the length of 1, whereas r, this has a length of r. And so what I have to do is I have to say r vector over the magnitude of r will give me a vector with a length of 1. And so that's what that means. So sometimes we can use this expression here, and sometimes it's much easier to use this expression here. And I've gone through a couple of problems where we use this r vector. In this case, we need to find the sine and the cosine in order to find the x and the y and possibly the z components. Right? In order to find the x, y, and z, we have to use our cosines. In this case, we don't. In this case, all we need to do is plug in the displacement vectors, and that sometimes is a lot easier than having to figure out what the sines and cosines are.